and how the waveform is going to be appearing for this DSB-SC signal, and then we have seen how to generate this DSB-SC signal. So, what are the methods to generate the signal? A balanced modulator and a ring modulator and chopper modulator that we are going to have. So, these are the methods of generating, and to detect it we have gone for coherent detection. So, what do you mean by coherent detection? What do you mean by coherent detection? Coherent detection. The carrier that we are generating at the receiving end should be in phase with the transmitted carrier, the FC that we are going to have it. And because there may be a change in the carrier that we are going to generate, because if we generate the same frequency with the two carriers, the frequency may be same, but the phases may not be the same. Therefore, the phase difference may be there. Therefore, we are going to have what we call quadrature nulls at the receiver. So, to avoid that, we are generating the carrier by the received signal itself, by going for a squarer, a divider, and a filter that we are going to have it. So, by using first you are squaring this input signal, then you pass through a filter and then divide it to give you the required carrier frequency in coherence with the received signal that we are going to have it, so that we can use that in the coherent detection and get back the original transmitted baseband signal. And what you call quadrature multiplexing also, because in the normal DSB-SC only one signal m of t can be transmitted by modulating by your cos omega ct. Whereas if you modulate another signal m2 of t with sin omega ct, because these two signals are in quadrature, they will not interfere with one signal with another signal, but whereas two signals the same bandwidth of 2 FM will be able to transmit the signal, so that at the receiving end out with a quadrature receiver and in phase receiver that we are going to have it, so that we can get back both the transmitted signals m1 of t and m2 of t. So, before going to the other type of modulation that we are going to have it, why you are gone for DSB-SC signal compared to AM modulation, wherein the receiver is going to be a simple diode envelope detector is enough. So, a diode and a resistor capacitor is combination is enough to detect your amplitude modulated signal, but we have gone for DSB-SC signal generation. Why you have gone for the DSB-SC signal? Power that we are going to generate or transmit in the case of AM is going to be carried by the carrier itself 67%, whereas the information content is only in the remaining 33%. Therefore, this 67% is a waste, therefore, we have suppressed the carrier. But what about the bandwidth requirements for both the AM and DSB? So, both the modulation techniques, the amplitude modulation and DSB-SC, requires 2 FM. Therefore, one signal requires 2 FM as the bandwidth that we are going to have it. Therefore, we have not got any reduction in the bandwidth, whereas we could reduce the power required to transmit to have a required efficiency. Whereas now, as you have seen that why you are transmitting only DSB-SC, because information is contained only in the sideband. So, we are transmitting the sidebands and suppressing the carrier, because there is no information in the carrier. Whereas we have in the sidebands, one with omega c plus omega m and another one with omega c minus omega m, or fc plus fm and fc minus fm, and both these sidebands are having the frequency of fm that we are going to have it. Therefore, even if you transmit only one sideband, either you have fc plus fm you transmit or fc minus fm, by having a coherent detector at the receiving end, we can get back the original signal or your baseband signal. Therefore, instead of transmitting two sideband, that is double sideband, we will be suppressing one more sideband also, so that we will be transmitting only one of the sidebands. So if you say that Fc plus Fm, we are saying that is the upper sideband, and Fc minus Fm corresponds to the lower sideband. Therefore, instead of transmitting both this upper sideband and lower sidebands, we will be transmitting only the upper sideband or one of the lower sideband and able to get back the original baseband signal that we are going to have it. So therefore, we are transmitting only one sideband. That's why we call this as a single sideband modulation. Only that of a single sideband modulation that we are going to have it. So what is this SSB signal that we are going to have? Right. A single sideband transmission only instead of that of a double sideband or that of your AM modulation. And not only the bandwidth reduction, you have in the DSB-SC 33% you have to transmit out of the total 100%. Whereas if you transmit only half of that, that means only around 17%, 16 point odd, 17% power only is sufficient to transmit the total information that we are going to have it. Therefore, in the case of SSB, you are going to have the advantage of power and the bandwidth also. Whereas in the case of DSB-SC, you have only that of your power efficiency are improving. Whereas in the case of SSB, we are getting the bandwidth reduction also. Next slide. So this is our required signal to be transmitted with a maximum frequency content of FM that we are going to have it. So we have 0 to FM as the required frequency to be transmitted baseband signal. So this we are modulating. Next slide. With a carrier of omega c. Therefore, we are getting Fc to Fc plus Fm and Fc to Fc minus Fm. These two signals are generated. One is the upper sideband and another one is the lower sideband. Here we have a DSB suppressed carrier signal that we are going to have it. We already suppressed by going for a ring modulator or that of a balanced modulator that we are going to have it. So here we are having only the frequency components of Fc to Fc plus Fm only. That is the upper sideband only we are going to consider here. So this is the frequency domain representation of your upper sideband. The previous one is a DSB-SC signal. The previous one is your baseband signal spectral domain representation. Next. This one is your lower sideband signal that we are going to have it. So we are having either a upper sideband or lower sideband to be transmitted, and this is what your frequency domain representation of your modulated signal. The upper sideband or that of your lower sideband, or basically we call this as SSB signal generation or the transmission that we are going to have it. So coming to our time domain representation, how do you represent your time domain signal that we are going to have it? And as you look into this LSB or USB or other things, what is that we are doing? We are transmitting only one sideband, Fc to Fc plus Fm only. So in the entire spectrum from minus plus infinity, we have only one band of frequencies, Fc to Fc plus Fm only, or Fc minus Fm to Fc, the lower sideband. So we are having only a band pass signal that we are going to have it. When this 2 over Fm is very small compared to our carrier frequency, we may say that this is a narrow band signal, because bandwidth of the overall transmitted signal is going to be very, very narrow, because 2 of Fm is much less than our carrier frequency Fc. Therefore, we are having a band pass, narrow band signal that we are going to have it. So, how to represent this frequency domain into a time domain representation that we are going to have it. For this one, we will go to the help of Hilbert transform and the representation of band pass signals with respect to that of your time domain signal that we are going to have it. So, what is the Hilbert transform? What is Hilbert transform? Given m of t, what is the Hilbert transform of this signal? Convolution of, so m of t convolved with 1 by pi t. Any other way of saying what is the Hilbert transform? One thing is your signal is convolved with another signal 1 by pi t. So that if you say that you have this m hat of t, the Hilbert transform of m of t as 1 by pi integral g of tau by t minus tau d tau. What exactly we are doing by saying that we are Hilbert transforming the signal? We are having a phase shift. How much phase shift? So compared to your m of t, all the frequency components of m of t are shifted by 90 degrees in the phase to get you our Hilbert transform, or this is m tau. So m of t you can get it as 1 by pi integral m hat tau t minus tau d tau. So this is the inverse transform, the Hilbert transform, and the another one is the inverse transform that we are going to have it. So we are having a 9 degrees phase shift. What will be the transform of this m hat of t? When you say that m of t and m of f are the Fourier transform pair, what will be m hat of t? M of t, m of f. What modifications are there? What is the transform of 1 by pi t? So this is minus j signal function of f. Therefore, what is m hat of t? The convolution of n by pi t with respect of m of t. So we have a convolution in the time domain. Therefore, you are going to have a product in the frequency domain. Therefore, minus j signum f m of f that we are going to have it. So this is what our frequency domain representation of Hilbert transform of the signal m of t. What is signal function? Minus 1. F less than 0. There is no t here. This is the frequency spectrum that we are putting. So is 0 if f is 0 and 1 if f is greater than 0. Or you can say that 1 and minus 1. This is what your signum function. Positive is 1, negative frequency corresponds to minus 1. So this is what we have studied about the Hilbert transform when we are talking about the signals and systems. Now let us say that we will define some function, a pre-envelope function that we are going to have it as g plus of t, that we are going to have it as that of g of m plus of t, because we are having signal m of t. So we are defining the pre-envelope of the signal m plus m of t, and this will be equal to m hat of t m of t plus j m hat of t. So we are defining a function g plus of t, defining as pre-envelope of the signal m of t. So m of t plus j m hat of t, that is the E. Signal plus j times the Hilbert transform of the signal. Therefore, what will be m of t? The real part of the pre-envelope that we are going to have. So that we want to get back our SSB signal, which is going to be our band pass signal. How we have to represent in the time domain function that we are going to have it. So we are having this g plus m plus of t as m of t plus j m hat of t. Suppose if you say that m plus of f is the transform of m plus of t, then what will be m plus of f? This will be equal to m of f plus j minus j signum function of f m of f. Okay? So plus j into minus j. So this is equal to 1. So m plus signum function of m of f. Therefore, your m plus of f will be equal to 2 m of f for f greater than 0. Because f is greater than 0, this is equal to 1 j sin signal function of f. So j and j cancels out and only have mf plus mf. 2 mf that we are going to have it. When f equal to 0, the second part is 0. Therefore, you have only m of f. And because this is f is equal to 0, we are having m of 0. This is not m of f, m of 0. That is the m of f at f equal to 0. What is the DC component of the spectral domain that we are going to have it? M of 0. And 0 for f less than 0. So this is the pre-envelope of the signal that we have defined. So what does it give rise to? Suppose if we have this is our baseband signal, m of 0 from 0 to fm, right? What is this? This is your frequency domain representation of m of t. So what will be our m plus of f? and after FM this is 0, and for negative frequency of this one is 0, right? So this is what the spectral representation of your pre-envelope that you have defined. So when we have this minus FM to plus FM, your baseband signal, the pre-envelope has come only to 0 to FM. The negative part has been made 0 by defining this pre-envelope signal that we are going to have it. Okay? Because this, from this will extend to our band pass signals. How we are going to have our band pass signal representation of time domain function, and from that we will derive what is going to be our SSP signal that we are going to have it. So this is what your pre-envelope spectral domain representation that we are going to have it. Now let us say that we have a band pass signal. A DSBSC signal. This is our band pass signal that we are going to have it. For this band pass signal, let us define this pre-envelope of G plus of t as G hat of t exponential omega ct. Where G of t is a complex function that we are going to have it, both imaginary and real parts that we are going to have. So we are having, this is our G of f for the signal G of t, having frequency components Fc minus Fm to Fc plus Fm that we are going to have it. And for this one, we are going for a pre-envelope. So when we have these two spectral lines, spectrum, what will be our pre-envelope signal that we are going to have it? So when we have minus Fm to Fm, we have only 0 to Fm with twice that of the total magnitude. In a similar way, this spectrum becomes this is our G of 0. Actually this is 1 by 2 also will be coming, because when you multiply DSBSC signal, half also will be coming. Anyhow, forget about the coefficients. So M of G of 0 you are going to have it. So you are going to get twice that of that with negative frequencies being 0. Your pre-envelope signal that we are going to have it. So this is what your G plus of f. Okay, we are having G plus of f, that is the pre-envelope of our signal G of t. And how we represent G plus of t? G hat of t multiplied with exponential signal. So when you multiply this with the exponential signal, you are having a frequency shift. Therefore, you will be having the spectrum will be coming as our required baseband signal with twice the magnitude that we are going to have it. So from the baseband DSB signal or a band pass signal, we have got into the required baseband signal. And what is our G of t? Is real part of G plus of t, right? And what is G plus of t? G hat of t into exponential function. And what is G hat of t? It's a complex function. Therefore, this G hat of t will write it as Gc of t plus j Gs of t, the real part and imaginary part of your G hat of t. Where the Gc of t, we are saying the in phase signal, and Gs of t as the quadrature signal, in phase signal and the quadrature signal. Therefore, what will be our G of t? Real part of G plus of t, and real part of G plus of t is G hat of t exponential. That is, this total real part of your G of t equal to into exponential of j omega ct. And what is this exponential of j omega ct? Plus j sin omega ct. And what is that we want? Real part only. So Gc of t into cos omega ct corresponds to real part, and plus j and plus j sin omega ct. So minus. Therefore, this will be equal to Gc of t cos omega ct minus Gs of t into sin omega ct. This is our required G of t for the band pass signal that we are going to have it. That's what we have started with. This is the spectrum of your G of f, or spectrum of your G of t. So in the time domain, we have got this as some quadrature signal Gs of t, and in phase signal Gc of t multiplied with cos omega ct and sin omega ct. Therefore, any band pass signal G of t can be represented in this way: Gc of t into cos omega ct minus Gs of t into sin omega ct. So this is how we are going to represent any band pass signal. And what is that we want? We want to represent a upper side band or a lower side band, which are the band pass signals only. What is the band pass of your upper side band signal? Fc to Fc plus Fm, whereas LSB is Fc minus Fm to Fc. So these are the band pass signals. Therefore, our SSB signal, which are representing as the band pass signal, a generated modulated signal S of t can be represented as Sc of t cos omega ct minus Ss of t into sin omega ct. Okay? because this is also a band pass signal. So this S of t I am representing as SC of t, which is going to be the in phase signal into cos omega ct minus quadrature phase signal into sin omega ct, that way I am going to have it. This is for upper sideband. For lower sideband this will be a plus. So if you say minus or plus, the upper sideband and lower sideband signals will be coming, whichever way you want it. Therefore, what will be our SC of t and SS of t? How to get these signals? SC of t and SS of t. Right. So that's what we are representing, the time domain signal as SC of t cos omega ct minus SS of t sin omega ct, where SC of t and SS of t are in phase and quadrature phase signals of your band pass signal, that we are going to have it. So we are having our band pass signal S of t, then we are multiplying with product modulator with cos omega ct or sin omega ct. Suppose if you multiply with cos omega ct, S of t into cos omega ct, what will happen? This is SC of t cos square omega ct minus SS of t into sin omega ct into cos omega ct. So this is having 1 plus cos omega ct. The other one is sin 2 omega ct. Right? Therefore, if you pass through a low pass filter after the product modulator, both the second harmonic signals will be eliminated, only that of your SC of t will be coming. Whereas if you have the signal as S of t, SC of t cos omega ct plus SS of t sin omega ct, because that is your lower sideband, that if you multiply with sin omega ct, then this will be giving you cos sin 2 omega ct, and this will be giving you cos 2 omega ct, and you are passing through a low pass filter, then you are going to get back your SS of t. Right? Therefore, by going for the product modulator and a low pass filter, we are going to get back your SC of t, the in phase signal, or the quadrature signal, that we are going to have it. That means with low pass filter, this ST SC of t will be equal to ST cos omega ct and ST sin omega ct gives you SS of t with half, okay, the scaling factor, that we are going to have it. But basically it is a proportional to your in phase signal and that of your quadrature signal, that we are going to have. Okay. So we want to find out this SC of t and SS of t in terms of your LSB or USB signal, that we are going to have it. Right, so that we can represent our overall band pass signal in the time domain derivation, that we are going to have it. So let us consider the upper sideband signal. So this is your upper sideband. Actually there is no carrier signal, that's why I am putting dot. If you put a straight line, that means a carrier also is present, but we don't have a carrier. That's why I'm putting as a dotted only. But minus Fc to Fc plus Fm, you have all the frequency components. This is what our S of F. Right? This is our upper sideband frequency domain representation. And we want to get your SC of t or SS of t. That way we are going to have it. So what is SC of t? S of t multiplied with cos omega ct. Therefore, what will be SC of F? Frequency domain representation of in phase signal. S of plus S of at what points? Between Fc to Fc plus Fm only. Therefore, otherwise this is going to be 0. Right? So this is minus Fm less than F less than Fm. Therefore, what is S of F minus Fc? When F equal to Fc, it is 0. That means your 0 axis, this is 0. Now this has been shifted to Fc. This 0 we are shifting by Fc because this is F minus Fc. Right? Therefore, this is Fc. And this is 2Fc, let us say. Fc and 2Fc. That means this we are shifting towards right. Therefore, so this is your S of F minus Fc. This is 0. Okay? What is S of F plus Fc? So this is shifting towards left. Therefore, we are going to have minus Fc minus 2Fc. Okay? S of F minus Fc, and this is S of F plus Fc. When you combine these two, we are getting our S of F with half. Okay? Therefore, when you combine this, we are going to get these two, 0 minus Fm and plus Fm minus 2Fc and plus 2Fc. Minus 2Fc minus Fm, and this is 2Fc plus Fm. and this is 1 by 2 of m of 0, s of 0. Because when you multiply this cos omega ct, half of that will be coming. And this is the spectrum of your SC of f. And what is that we are doing? We are passing through a low pass filter. Minus FM2 plus FM. And what is this? But with a carrier of 2FC. Right? This is SSB signal with a carrier FC. Whereas these two lines corresponds to SSB signal with a carrier of 2FC. By passing through a low pass filter, only this will be passed through, eliminating these spectral lines. Then what will be the output? Only this output. Therefore, what is the output that we are going to have it? SC of f after low pass filter will be equal to one by 2 m of f, or your SC of t 1 by 2 m of t. Okay? Any doubts here? Because we have to extend similar way for SCS of f also. Shifting towards right and left, and then multiplying, and then summing up. Okay? So this is what your in phase signal time domain function is correspond to your m of t. Okay? So in this SC of t is proportional to your m of t. Okay? Because this is what we have obtained with all the frequency domain representation and your 3 envelope representation and band pass signal representation that we are going to have it. Whatever we have discussed with the transform, Hilbert transform, then we have seen what is the pre-envelope and then band pass signal. So from that we have got this as our required in phase time domain signal of your band pass signal coefficient SC of t, which is going to be of m of t. Then what is your S of f? This is S of f minus fc, and this is S of f plus fc. Whereas what is SS of t? S of t sin omega ct. Therefore, your SC of f will be equal to J times S of f minus fc minus S of okay, because we are multiplying with sin omega ct. Refer back to your Fourier transform properties. The f of t into cos omega ct and f of t into sin omega ct. That's what you are represented when we are talking about signal systems Fourier transform. So f of f minus fc plus f of f plus fc for your cos multiplication, and for sin j times, because that by 2j is going to be there in your sin omega ct Euler's formula. So that j will be coming here. Then you are going to get the required one. So what is the difference? So this minus this, right? And 1 by j. Because j is this side, so I am tapping all of this. 1 by j of S of f is this. So for positive frequencies, if I multiply with signum function minus signum function, what will happen? This becomes positive. Minus becomes positive, and this will be the same. Because minus into minus only plus. That way I are going to have it. Therefore, when you multiply this with a signum function, so what we are having is m hat of t. So s of f will be equal to minus j, because minus signum function we are going to multiply. So j is there, minus I am putting signum function of f, and when I multiply with signum function, this becomes positive. Therefore, this is going to be our m of f. And what is this? Hilbert transform of your m of t, because minus j signum function, and this is m of t, m of f. Therefore, pardon? S of t, m hat of t. Anyway, as we have here 1 by 2, here also we are going to have the 1 by 2, because we are multiplying with cos omega ct, cos square omega ct. So that 1 by 2 will be coming. Okay. Therefore, here also we are going to get 1 by 2 m hat of t. And pass signal USP, we are having SC of t is proportional to m of t, and your SS of t is proportional to m hat of t, or Hilbert transform of your m of t. Therefore, this is the frequency domain representation of your ESP signal, the upper side band, and your S of t will be equal to m of t cos omega ct minus m hat of t sin omega ct. This will be the time domain representation of your USB signal. I am not taking into correspondence the factors 1 by 2, because anyhow you can take out S of t as half of S of t. Finally, it is only the multiplication factor that we are going to have it throughout, so I can take out and make it a constant and then eliminate it. So basically, your ESP signal S of t, the time domain representation is m of t into cos omega ct minus m hat of t sin omega. M of t is your baseband signal, your cos function is your carrier signal, right? And for the LSB, S of t will be equal to m of t cos omega ct plus m hat of t sin omega ct. Right? That's what your domain representation of your LSB signal, the lower side band. So by considering this as band pass signals, we have derived that, got the time domain representation. This is how we have to derive the time domain representation of your band pass signal, ESB or LSB that we are going to have. The other one is your frequency domain, simple representation that we are going to have it, but the time domain representation is involved one. You have to start with your 3 and up, then band pass signal, then all this multiplication, shifting of the frequency spectrums, adding and subtracting, and getting the equivalent time domain functions along with the frequency domain representation of your SC of f and SS of f. Therefore, these two are your time domain representation of ESB and LSB that we are going to have. So this is what your expressions for your LSB or ESB. And if you are asked to have a frequency domain representation, anyhow, a simple spectral domain FC to FC plus FM or FC minus FM along with a negative domain frequencies also. You have that representation, negative frequencies and positive frequencies. That gives you your frequency domain representation. SSB signal that we are going to have. How to generate the SSB signal? Because this is what we have got it, but we want to generate the signal. So SSB generation. So basically we are having two methods. Filtering method or frequency description method and phasing method or phase description that we are going to have. Filter method or phasing method. Filter method. This all we have already seen that. In the filtering method, what we are doing is we have the DSB signal by a product modulation, right? Therefore, you have a product modulator or a balanced modulator, m of t and cos omega ct the carrier. Okay? So this is what your DSB-SC signal, a product modulator, and actually this is a balanced modulator, because product modulator may not suppress your carrier signal, whereas balanced modulator is going to suppress your carrier signal also. So simply you say that when you say product modulator, because this is a product of these two signals, m of t into cos omega ct, that's what we want in the case of DSB-SC signal. So this corresponds to m of t into cos omega ct, and the frequency domain representation is this, both the side bands. Then we have a band pass filter. This will be our SSB signal, a band pass signal. After balanced modulator, you have a band pass filter. A band pass filter with FC to FC plus FM gives you upper side band, and FC minus FM to FC gives you the lower side band. So whatever the one that you want, you design your band pass filter accordingly to give you your LSB or USB, not SSB. USB or LSB, or in general SSB signal. Okay, not USB or SSB. USB or LSB, or get the required SSB signal, upper side band or the lower side band. So this appears to be simple, but what is the problem here? So we have a baseband signal, let us say signal, a Y signal that we are going to have it. So normally we say that some 30 hertz to 20 kilohertz, or basically 4 kilohertz, we may say. And suppose we are using a carrier of 10 megahertz, right? The carrier frequency that we are going to have it is 10 megahertz. Then what will be the spectrum that we are going to have it? So 10 is it okay? Okay. 10 into 10 to the power of 6 plus 30 to 10 into 10 to the power of 6 plus, let us say, 3 kilohertz, because higher frequencies doesn't carry much energy, therefore I am restricting up to 3 kilohertz. And what is the lower side band? This is 10 into 10 to the power of 6 minus there is no much difference between the guard band, only 60 hertz with the overall carrier frequency of 10 kilohertz. That means the percentage is 0.006%. That means you should have very, very sharp cutoff filters to eliminate the other side band. Your band pass filter, you have to design very, very sharp cutoff filter, so that the and with this small variation between these two side bands, it is difficult to design your band pass filter to have required cutoff. Therefore, this will not be of use. What is that we can do? Instead of going for a single stage conversion to get your required carrier frequency, you have number of stages, and This also, even though we say that it starts from 30 hertz, at this will be having 300 hertz to 3 kilohertz. The maximum energy is going to be contained in this frequency spectrum. So eliminate the low frequencies and discard the high frequencies. Pass only 300 to 3000 hertz as your required voice signal. Because remaining things you can eliminate it because the energy content is very small. So more than 90% is going to pass in this 300 to 3 kilohertz. The signal that we are going to have it. So you can get back the original signal with less distortion that way. Say that this cos omega C1, some other carrier frequency, I have made it as 100 kilohertz, right? Then what will happen? This is 100.3 to 103 is the upper side band, right? And this is 99.7, 97 to 99.7. So we have 600 in percentage band that we are going to have it compared to 0.0006 that we are going to have it, where then you can't design the required filter to eliminate one of the side band, whereas with this you can design the circuit to pass only one of the side band. Now what is the baseband signal, band pass signal? 100.3 to 103. This you multiply with 10 megahertz carrier. So not from 300, this is 100.3 is your starting point. So that means the band difference 200 kilohertz at 10 megahertz carrier frequency that we are going to have. Therefore 0.2% is the cutoff frequency variations that we are going to have, whereas previously we are having 0.0006. Therefore you can't design this, but whereas this will be able to design. If still we have any problem, you may be having one more stage, 100 to 1 megahertz, 1 megahertz to 10 megahertz, and so on. Number of stages you increase it so that you can design the required filter sideband signal. If you are transmitting USB, LSB is your unwanted signal. If you are transmitting LSB, ESB is your unwanted signal that we are going to have. Okay, so this is the drawback in the filter method. Straight away you can't have the carrier, required carrier here for the first stage, but you will be having number of stages, 2 or 3 stages that we are going to have it to give you the required filter design that we are going to have. Okay, so this is what we are going to have as the filter method of generation or frequency discrimination of method of. Okay, what is the other method that we are going to have it? Phasing or phase discrimination, frequency discrimination and phase discrimination. Okay. Frequency discrimination and phase discrimination. So what is that phase discrimination method that we are going to have it? And this is our time domain representation of your baseband signal. S of t equal to m of t cos omega ct plus or minus m hat of t sin omega ct that we are going to have it. So you have your carrier generator cos omega ct and have a 90 degrees phase shift sin omega ct, right? And you have your m of t and have a Hilbert transformer to give you m hat of t. These two signals we are generating. So we are having your m of t, the baseband signal. That straight away I am giving to one of the product modulator or your balanced modulator along with your oscillator generated cos omega ct. The other one is wide band 90 degrees phase shifter. Why you are calling it wide band? Because all the frequency components m of t should be shifted by this 90 degrees phase shift. Whereas it is easy here for oscillator output cos omega ct, there is only one frequency omega c, and getting 90 degrees phase shift is very easy, and we are getting required sin omega ct. Whereas getting Hilbert transform or 90 degrees phase shift for all the frequency components is not so simple, but let us say that we have that frequency phase shifter that we have it, then we are having m hat of t. So we are having two product modulators. So we are having a phase direct signal that we are going to have it. Another one is phase shifted signal, 90 degrees phase shifted signal with the two product modulators that we are going to have it. So when we have this in phase path, you are going to get m of t cos omega ct, and in the quadrature path you are getting m hat of t sin omega ct. In the summation, if you have here minus, you are getting upper sideband signal because plus and minus in phase minus quadrature phase, you are going to get an upper sideband signal. Whereas in this plus or minus, if you have a plus, then that gives you an LSB signal that we are going to have it. So this is how we will be having a phase discrimination method of generating your SSB signal, right? But here, as we are saying, 9 degrees phase shift is not. So what is that we can do? Instead of shifting the entire thing, next slide, we are going to shift the input for both the product modulators. One gives you a phase difference of the frequency components by alpha, another one by a phase value of beta, so that the phase difference between these two, beta minus alpha, equal to pi by 2, right? The phase difference between these two networks, the beta minus alpha, is going to be pi by 2. Therefore, if you say that alpha network is in phase, the beta network is 9 degrees out of phase. That's what we are having, m of t and m hat of t, that what we have got is in phase and quarter phase signals that we are going to have it. So if you say that one is in phase, the other one is quadrature phase, so you are going to get the required SSB signal for this alpha and phase angle network, so that both gives. Whereas this 9 degrees phase shift for oscillator frequency is so easy, because there is only one frequency, you can get a 9 degrees phase shift for your cos omega ct to sin omega ct beta. Whereas m of t, the previous method block diagram that we have seen, is not going to be giving complete phase variation of pi by 2 for all the frequency components. Therefore, we may not be exactly getting your required SSB signal. Whereas this alpha and beta, because if alpha is not getting the exact value, beta also not going to give the same difference that we are going to have, but difference we are maintaining as pi by 2 only. That we can design. Okay. So if beta is changing, alpha is also changing. Therefore, beta minus alpha. That's how we are going to get the phase discrimination method, and this we are calling as Hartley model. We are going to have it. Okay. The third method that we are going to have it is what you call we have again without any shift in these frequencies, we have this two modulators, and we are having a low pass filter. Then you have another product modulator and giving you the required. Don't have it. One thing is there are constraints on the frequencies that we are going to have it. Next slide. So we are having a required baseband signal between FA and FB, so that the low pass filter that we are designing, we are going to define as FB minus FA by 2 is for 1, and for FC greater than FE by 2 that we are going to have it. So and FB we are designing such that having this criteria that we have. Once you have this, then we are going to get the required with plus and minus that we are going to have it to give you the required ESB or LSB signal that we are going to have. You know, you go through the entire to show that this gives you the required SSB time domain signal with this FA and FB frequencies that we are going to have. The cutoff frequency of the frequency is FB minus FA by 2, and whereas the carrier frequency is much larger than this cutoff frequency that we are going to have. Okay, so this is the third method, or what you call Weaver's method of the signal. Three methods that we are going to have it to generate your single sideband signal. So once you generate the SSB signal, what next you want after transmitting, you have to demodulate or recover. Here we should have only a coherent detection that we are going to have it. When we have only a DSB-SC signal or SSB signal, because there is no carrier, we are going to go for only a coherent detection that we are going to have it. How to get the coherent detection? By generating a coherent carrier. Then passing it. Having S of t, which is going to be our required input SSB signal, or ESB signal that we are going to have it. That we are multiplying with your carrier signal cos omega ct, which we are generating as a coherent carrier that we are going to have it. AC cos omega ct that we are going to have it. So we are having a product S of t into cos omega ct that we are going to have it, and we are getting some signal V of t. So that we are passing through a low pass filter, so that higher harmonics are eliminated. Only that of MT is going to be passed through your low pass filter. Then you are getting your required V naught is nothing but your required baseband signal. So V of t is AC. Here. So your S of t is M of t cos omega ct minus m hat of t sin omega ct. What is that we are doing in the product modulation? S of t into cos omega ct. That means this is m of t t cos omega ct into sin omega ct. Therefore, this will be equal to m of t by 2 plus m of t into cos 2 omega ct by 2 minus m hat of t sin 2 omega ct by 2. This is our required signal. And what is this? The SSB signal with 2fc. What is the carrier frequency? And but because we are using a low pass filter, this will be eliminated, and your output V naught of t is your m of t by 2. That is your baseband signal that we are going to have. So by having a proper carrier that we are going to have it cos omega ct at the receiving end, you can recover the baseband signal. One thing is we require a coherent carrier, because if there is any change in the phase or the frequency, that will be multiplied with this m of t also, your cos phi. So that may be varying the what you call quadrature null effect or min and wane that we are going to have, increase or decrease depending on the phi value that we are going to have, and pi value cannot be constant also. So it will be changing for different times and different frequency components. Therefore, this m of t is going to be continuously changing, which we don't require that. Therefore, we require a coherent carrier to be generated. In the modification that we are going to have it, if we have a carrier also is going to be transmitted along with a DSB SC signal or that of your SSB signal. That carrier we are going to transmit sometimes. So how we are going to achieve the demodulation without that coherent detection that we are going to have? The disadvantage that we are having here so far is a coherent carrier how to generate any variations that may be reflected in the recovered signal, whereas we'll be sending sometimes a pilot carrier. So using that, you will be getting back the original signal without any coherent detection also. And what will happen if the phase variations are there and frequency variations are there, and how to go for the other type in the next class. Okay. And any doubts here? SSB and the frequency domain representation we have discussed for LSB, and then pre-envelope definition of the signal that we are going to have along with your Hilbert transform, and from that we have derived your time domain of m of t that we are going to have it. Then we have seen how to generate the signal or a phase discrimination method or the third method that we are going to have it. And in the phase discrimination method, the component may be difficult. Therefore, we are gone for two different phase generating networks that we are going to have, so that the difference you can maintain by beta minus alpha as pi by 2. Then we are going to get the required SSB signal generation that we are going to have. Then we have seen third method. Then we have seen how to demodulate our SSB signal by simple